A grandfather clock works by utilizing a pendulum and a system of gears to measure and display time. Such clocks are meticulously built from scratch, incorporating materials that expand at different rates when the temperature changes. In this video, we will explore the fascinating and unexpected consequences of this design choice on the clock's accuracy by solving a very classic physics problem on thermal expansion of materials and how it affects the time displayed by these clocks. Let's look at the problem. A grandfather clock is controlled by swinging a brass pendulum that is 1.6 meters long at a temperature of 33 degrees Celsius. What is the length of the pendulum? So we are looking for the length when the temperature drops to 0 degrees Celsius. Again, if the period of the pendulum is given by this equation, where L is its length, thus the change in length of the rod causes the clock to run faster or slow. And why is this happening? We are to take the linear coefficients of expansion for brass to be 19 times 10 to the power minus 6 per degree Celsius. Now let's look at the solution. So this is a problem on thermal expansion of materials, and specifically since we are dealing with a pendulum rod, we are going to look at linear expansion of this rod. And to solve this problem, we need to first take the data from the problem. So the data we can take is that we are given the initial length of the rod, which I'll call L0 equals 1.6 meters, and then we are also given the initial temperature of the rod, so Ti, that is T initial, 33 degrees Celsius. So we are to find the length of this pendulum rod when the temperature drops to 0 degrees Celsius, meaning the final temperature is now 0 degrees Celsius. We are also given alpha for brass to be 19 times 10 to the power minus 6 per degrees Celsius. And this alpha is a property of brass. And for any material at all, it has its unique alpha. And this alpha is called the coefficient of linear expansion. And what this physical quantity means is that it quantifies how much a material's length changes for a given change in temperature. Alright, so with this problem, a grandfather clock, which we can visualize to be, so we have a clock with a pendulum, and this is the pendulum ball. So this pendulum swings back and forth, go that way, and also go that way. So this pendulum swings back and forth, making a complete cycle when it moves from point A through point B, point C, and then back to A. That makes one complete cycle. However, this pendulum has some length, original length L0, which we are given as 1.6 meters in the problem. So applying the linear expansion of materials, any material when heated expands by some amount, which is given by delta L equals alpha, which is this property of the material. In this case, we are given alpha to be 19 times 10 to the power minus 6 per degree Celsius, multiplying the original length of the material and also the change in temperature. So this equation here is what we need to solve this problem, since we are looking at the linear expansion of this pendulum rod. So to solve for this problem, first we need to plug in our values. So we have delta L is going to be alpha, which we are given to be 19 times 10 to the power minus 6 per degree Celsius, and then L0, which is 1.6 meters, and then the change in temperature, which is the final temperature minus the initial temperature. So the final temperature is 0 degrees Celsius minus the initial temperature, which is 33 degrees Celsius. Now evaluating this, we can see that the degrees Celsius cancels. So we are left with delta L equals 19 times 10 to the power minus 6 multiplying 1.6 meters multiplying minus 33. Therefore, we have delta L to be approximately 0.0000304, and that is a minus value, meaning the length of this pendulum reduced. So by finding the delta L coming out as negative, what it tells us is that the length reduced. So this L0 has shrunk, and to find what is the final length, we know that this delta L here is simply L final, that is the L that we are going to find, minus the L initial. So that will give us final length to be the initial length plus change in length that occurred due to the change in temperature. All right, so this is the change in length, and we can see that the change in length is negative, indicating that the length shrank or it reduced. So the change in length equals the length minus the length initial. That is the final length minus the initial length. And we had that to be a negative value. Therefore, we can find the length to be L naught plus delta L. So substituting these values, we will have L naught to be 1.6 meters, and then delta L is negative, so it subtracts from that, indicating that the final length will be reduced. So minus 0.0000304 meters. And evaluating this will give us a final length of approximately 1599.0 millimeters. All right, so that is the length. And now let's look at the second part of this problem. It says if the period of a pendulum is given by t equals 2 pi square root of L over G, okay, what happens to the time, or what happens to the clock? Does it run faster or slower? So the period of this pendulum is if this pendulum starts from point A and then goes through point B to C and then back to A, makes one complete cycle. And for a pendulum or a swinging pendulum, the period is given by T equals 2 pi square root of L over G. Here we can see that the period is proportional to the square root of L. Thereby, increasing L increases the time it takes to make one complete cycle, and also decreasing L decreases the time it takes to make one complete cycle. Therefore, with this problem, since there's a decrease in the length of this rod due to change in temperature by the temperature reducing from 33 degrees Celsius to 0 degrees Celsius, then the length is now reduced. Thereby, the period is going to be reduced, meaning it is going to take a shorter period of time to make one complete cycle, and that significantly would affect the time. Therefore, the clock is going to run faster. All right, so this is a very interesting problem, and it gives us practice on linear expansion of materials. If you enjoyed this video, please like, share, and if you are new to this channel, subscribe to this channel. And until then, I'll see you in my next video. Thank you.